was just one question with many parts, is that right? Yeah. Well, we only have one lesson left and then we're finished for semester 1, which is good. Exciting, I know. Yes. Okay. Let me try and draw the picture. So, you have your grating, and then you have your, what colour light? Red, is it? Is that right? Red light? Please, somebody answer me. Was it red light? No. Was it red light? Why is nobody answering me? Did you try the question?
Yes.
Was it red light at the start?
Yes.
Thank you. Now, I think at the start, I told you how many holes there are here. Lines per millimeter, wasn't it? How many were there?
3 multiply 10 power 5.
Okay, so there is 300,000 lines per millimeter. That means each slit is equal to 1 over 300,000 millimeter. So that's 1 over 3 times 10 to the minus 8 meters, which is 3.33.
Why do you change it to minus 3 from 5? Change it to minus 3.
Yeah?
Why?
Oh, this is because these are millimeters. So this is a millimeter. Isn't it? 10 to the minus 3 meters.
Here is 3 times 10 to 5
Yeah.
per meter.
No, per millimeter. Oh, sorry, did it say per meter? Oh, I'm so sorry. So sorry. Per meter. Tekken, you didn't correct me.
Oh.
Per meter. Per meter. So this is gone. So this is minus 5. So this one here is minus 6. Or if you want, that's 3.33 micrometers. So that's the first part. Like this. Yes? What? What are you saying? Close the window? No, it's nice. It's fresh and cool and relaxing. It's what I need right now. Okay, this is the small d. If you look, that's the distances here. D, 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 etc.
How did you just do 1 over E?
Well, think about it like this. If I go to the side, look up please for a moment, everybody. So imagine I have 1 meter and there's 2 slits per meter. Then how big is each one, KJ? Divided by 2. And if I said there were 3 slits, then how big would each one be? divided by 3. So in other words, it'd be 1 over the number. So in this question I said there was, what is it, 1, 2, 3, 4, 5 slits per meter. So I need to do 1 over this number to get how many, or how big each one is. Yeah? Okay. Right, so that's probably part A. Tekken, what does part B ask?
Diffraction angle for the second order.
Okay, so do you see that's this one here? N equals 2. Oh, and do I give the frequency or the wavelength of the red light?
Yeah.
What do I give?
600.
Now, what is that?
Newton
Nanometer.
No,
Red
is it the
light.
frequency or the wavelength?
Wavelength.
Thank you. What do I say it is?
633 nanometer.
Thank you. 633 nanometers is the wavelength. Okay, so you know your formula here is n lambda equals d sine theta. So 2 times 633 times 10 to the minus 9 equals 3.33 times 10 to the minus 6 sine theta. So this gives me the theta now. What is that in degrees? KJ, you're going to get it. Thank you. And Taken, can you calculate this? Degrees mode? So theta is sine inverse 2 times 633 times 10 to the minus 9 over 3.33 times 10 to the minus 6. So theta is 22.3 degrees. Okay, what's next? Part C.
The highest order diffraction line that is observable with this red light.
Okay. So the biggest one, well, if you think about it, theta must be less than 90 degrees. So put it in red here. So, theta must be less than 90 degrees. So that means sine theta must be less than 1. So then that means n lambda must be less than d. So that means n must be less than d over lambda. So then that means n must be less than 3.33 times 10 to the minus 6 over 633 times 10 to the minus 9. So what do we get here? N must be less than? Well, let's see. What do we get? That's 1,000, isn't it? 1, 2.
5.26.
So the biggest n maximum is 5.
It must be whole number.
Oh yes, definitely. What do I ask in the next part? Is that the one with the blue light?
The red light is replaced by a blue light
Yeah.
of wavelength 506.4 nanometers.
Yeah. This is the wavelength of the blue light, okay?
And it's found that the diffraction angle for some order of the red light coincides exactly with the diffraction angle for the blue light in the next order spectrum.
Yes. Now read that again, but a bit slower so I can draw it on the screen.
It is found that
Not that slow. It's okay, thank you.
the diffraction angle for some order of the red light coincides exactly with the diffraction angle for the blue light in the next order.
Okay, let's have a look. So what it's saying here is, here for example is the order of the red light. N0, N1, N2, and N3. And when you take along the blue light, N equals 0. And maybe for example here, whatever, N equals 1. I don't know. N equals 2. N equals 3. And then here, maybe on this one, the two of them match. The question says that for some value for order for red light, the blue light in the next order, that means one higher, will match. So for example, if n equals 1 for the red, then n will equal 2 for the blue. So here here at 0 they match, but here at 1 they don't match, they don't match, they don't match at 3, but let's say they match at the fourth blue light. So that's what the question is saying. So our job now is to see what we can make of that. So I'm just drawing this to help explain the idea. If I go back to the question. So what you have here, you have red and you have blue. So for the red, what was the wavelength for the red? 633 nanometers, and for the blue it's 506 nanometers. The n we don't know, I'll call it x, and here the n we don't know, but we know it's x plus 1. The d we know, it's what was it? 3.33, wasn't it? And the theta we don't know, we'll call it theta. And the theta here we don't know, but we know it's the same angle. Okay, so we have on the left here n lambda equals d sine theta. N lambda equals d sine theta. So if I bring the d down, and if I bring the d down, I get n lambda over d equals n lambda over d. The one on the left is for red, and the one on the right is for blue. Also the d's are the same. So actually that means those d's cancel as well. Actually, sorry, yeah, I could have just kept it like this. This is the same as this because the thetas are the same and the d's are the same. So you get n for the red, lambda for the red equals n for the blue, lambda for the blue. So for the red, that's x 633 nanometers, and for the blue that's x plus 1 506 nanometers. The nanometers cancel, so you get 633x equals 506x plus 506. So you get x equals 506 over 633 minus 506, which equals, what's that please? Like 5? Or 4?
3?
3?
4?
Which is
3.98.
3.98, okay, so 4. So you have here the fourth order red will match the fifth order blue. Yes. What's the next question asking now? The angle, is it?
Yeah, determine the diffraction angle for the second order of blue light.
Which part is this? E?
E.
Now the E is the same as B, the only difference is it's blue light, so you just need to change this number. What's the wavelength for the blue light?
506.
Yeah, so the only difference is that gets changed to 506. So 2 times 506 times 10 to the minus 9 over 3.33 times 10 to the minus 6. So this one is for the red. What is it for the blue?
$17.69.
17.69 degrees. Again, I'm just using this formula here. Yeah. Okay, so if I, the next part F is about the white light, isn't it?
The fringes were red in part A and then, of course, blue in part D.
Yeah, it's that one. It's okay. Right, so here when you had your red light, there's a dot here, and then for example there was a dot here. And what was the angle for the second dot, n equals 2? What was it? 20 something? 22.3 degrees. And what was the angle for the second dot for blue?
17.
So that's a little bit smaller, isn't it?
Yeah.
So here's the one for blue, and then here's the one for blue as well, and here's the one for red, and then here here is the ones for red and blue there. So what you'll notice is that the red is an angle is a little bit bigger than the blue, and this actually happens at each order, at each fringe. If you replace this with white light, you get all the colours: red, orange, yellow, green, blue, indigo, violet. And here when you look at the dots, you get red and blue in this order. If I put in some orange light, it won't surprise you if I tell you that the orange light will be here. So in fact, if you put white light here with all the 7 colours, what you'll see here is 7 colours also in the same order: red, orange, yellow, red, orange, yellow, green, blue, indigo, violet. That you'll get a little rainbow here of colours. And the reason for this is it's down to this formula: n lambda equals d sine theta. So theta equals sine inverse n lambda over d. So what happens when we make the lambda smaller? then this one here gets smaller. And the difference between this and this is the lambda here is smaller than the lambda here. So this is why the angles are a little bit different, because the wavelengths are a little bit different, which means the colors will be in slightly different places on the screen. So, do I have it the right way around? Yeah, if this is small, then this is small. Oh, sorry, did I? Yeah, that's right, isn't it? Yeah, this one. This is the smallest wavelength, and this is the biggest. So that means this one, the red, will have the biggest angle. Then the orange will have the next biggest, and so on. Blue is somewhere in the middle. So there'll be a rainbow here with red on the outside and purple on the inside. So we get a rainbow at each fringe. Red at the outer part, purple at the inner part. And that's the answer for that one. The good thing is this question doesn't change too much in the exam, because there's not too much they can ask you. So if you can do this question, then you can really do all the questions on this topic. They're not too different. It'll usually be just like this, the question. The only formula I didn't use was what was it? What was it? Lambda d over d, wasn't that it? Lambda d over d, yeah. So I might as well calculate this to see what I get. Part G. So let's do it for the red light. What was the lambda? 633 times 10 to the minus 9. Oh, I didn't tell you how far away it was, did I? Did I? Let's just make up a number. Let's make our life easy. Let's say it's 1 meter away. Okay, and what's the small d? What's the small d? 3.33, was that it? Times 10 to the minus 6? Okay. What's this, so? Zero point. Okay, so 20 centimeters. What did I say the maximum order was? 5, wasn't it? So if I just go down for, can I go down? No, not yet. Yeah. So I said the maximum order was 5, so that means it's like this. N equals 0, 1, 2, 3, 4, 5. And here, 1, 2, 3, 4, 5, minus 5. So you have 1, so that's S, 2, 3, 4, 5, 6, 7, 8, 9, 10 S's. So the total distance from the first and last red dot, this is red here and this is red here, that will be 10 s's, which will be 3 meters. So the light will spread out, but it's not going to go past 10 meters.
Why?
Well, we just worked out the maximum order. It was n equals 5, wasn't it? And the distance between each fringe is 30 centimeters.
20.
Oh, 20, is it? Sorry, I thought it was sorry. So then this is 2 meters.
Why is it 2 meters?
Huh?
Why is it 2 meters?
10 s's. Because the maximum is 5 to minus 5. No?
Okay.
There's 10 s's there, isn't there? So it'll be 10 times 20 centimeters. These are all red dots. 5th order, 4th, 3rd, 2nd, 1st, 0, 1, 2, 3, 4, 5. And then there's no more and no more. Okay. You may close it. Okay. You got all of that? Yeah. And stop.